la verdad que lo disfruto mucho.
Ok, pues yo creo que ya puedo hacer el anuncio, ¿no, Carlos? Okay, well, so thank you everyone for coming. Welcome to this new session of our category seminar. We're very happy to introduce today's speaker, Roberto Hernández Palomares from Ohio State University, who will be speaking to us about tensor categories and C-star algebras. So the title of his talk is Actions of Unitary Tensor Categories and C-star Algebras. I would like to encourage everyone to make questions at any time during or after the talk. Questions can be asked in Spanish, and of course, Roberto can answer them in Spanish or English as he wishes. So please, Roberto, take it away. Thank you very much.
Thank you, Juan. Also, thank you, Carlos, for inviting me to being here. As I was saying, it's really a great pleasure for me to speak here. So yeah, today I'll talk about actions of unitary tensor categories, UTCs, on C-star algebras. And since I'm a bit of a foreigner or an outsider to category theory, I really just found it as I was doing operator algebras. I really want to take advantage of that. And since also this is a seminar in category theory, I would like to introduce all those ideas from operator algebras at an intuitive level and perhaps push as many analogies as I can possibly find between the constructions I'll be showing you and perhaps constructions arising in category theory abstractly or algebra to make it perhaps more accessible for the audience. Again, if there's any questions, please, or comments, please interrupt at any time. So about the overall structure of my talk, I think I can roughly divide it in two parts. An introduction where I will introduce what unitary tensor categories are very briefly, not to bore everyone in the audience, but perhaps to establish a bit of the notation and reveal how I think about categories, what I think of when I say UTC. And then basically what I want to describe as a deep interplay or some of the bridges that's been built between subfactors and unitary tensor categories. I will tell you what a subfactor is. I'll be just talking about von Neumann algebras in a second. And the main idea I want to convey for the first half of my talk is that subfactors have quantum symmetries and that we can properly formalize that idea using actions of unitary tensor categories on von Neumann algebras. Now, for the second leg of the talk, I'll be transitioning to C-star algebras. And I think I want to smoothen out this transition by somehow comparing the two perspectives, what can be done in von Neumann algebras that just doesn't happen, or it's just harder to achieve in C-star algebras, and then address a question about existence of quantum symmetries in C-star algebras. That's some joint work that I wrote down with Mike Harkless last year. And I want to close my talk by giving you some perspectives, perhaps giving you a quick narrative on what the horizon for the discipline of C-star algebra from a quantum symmetries point of view is, and probably convince you that you should care about the programs I will speak about. Okay, so let me get started. Can you guys see me scrolling up and down? I think we checked that earlier. Okay, awesome. So unitary tensor category is here. I'll be kind of loose about my formalism, but maybe I'll be a bit loose in my rigor, but probably more effective in conveying an idea. So for a unitary tensor category, I understand a tuple consisting of a semi-simple C-linear category. So I just have a countably semi-simple category whose Hom spaces are vector spaces. And this comes equipped with a tensor product bifunctor. So that allows you to multiply, in a way, objects and morphisms. And since you want this operation to be associative in some categorical sense, you have to choose some associator morphism, giving you what's known as the coherence data for the category. And you also have a chosen monoidal or tensor unit for your tensor product. And I will not really speak about coherence in this context, but the one axiom that will be relevant for us is the pentagon that basically tells you that if you parenthesize an expression A times B times C times D and move parentheses around all the way from a leftmost parenthesization to a rightmost parenthesizations in either this or the other possible ways, the the associator morphisms give you some sort of coherence. So really you're allowed to define more than just the product of two objects or two morphisms using these associators. So this is a tensor categorical structure. So where does the unitarity come from? What do I mean by that? Well, there's a bunch of properties and structure I want my category to have. And for instance, I demand that every endomorphism algebra, which I will denote by C of C, C an object, is a finite dimensional C-star algebra. Also, I demand that every object has a unitary dual, which I will denote by C bar, and also that every object has a pre-dual. This means that you have a C check such that if you dualize it, you recover something isomorphic to C. Really, I think the practical way to think about tensor categories, unitary or not, is by playing with string diagrams or the graphical calculus, where, for instance, here I have four morphisms, which I'm denoting by coupons, and strings are labeled by objects in the category. So, for instance, F1 is a morphism that connects B1 to C1. I'm reading bottom to top. G1 is a morphism from A1 to B1. So here, what I'm showing is some graphical calculus representing what's called as the exchange relation. And I'm combining the operations of vertical composition, which is just the composition of Homs, and the tensor product, which is horizontal composition pictorically. So you could interpret this diagram, say if you split it with a vertical line on the in the middle, you would recover, for instance, F1 composed with G1 in this order, times horizontally F2 composed with G2 horizontally. But you could also slice it horizontally through this tensor product operation right here and get F1 tensor F2 composed with G1 tensor G2. And of course, both expressions are equivalent. So this expression is very, very powerful when playing with the graphical calculus of tensor categories. And of course, this whole diagram denotes morphism connecting A1 tensor A2 from A1 tensor A2 to C1 tensor C2. So enough about tensor categories. That was probably the easy part for you guys. Let's now talk about subfactors. So a von Neumann algebra is a nice operator algebra in a sense that you can regard it as some nice subalgebra of bounded operators on a Hilbert space. And by nice, I mean that you can algebraically characterize it as A equals its double commutant. So A equals the centralizer of its centralizer algebra, which is completely algebraic. If you're given a von Neumann algebra, you will always be able to decompose it as a direct integral of simple von Neumann algebras. So making the theory of von Neumann algebra semi-simple in that sense. Simple von Neumann algebras typically are called factors, right? And if you want to study factors maps between factors, that really amounts to studying just injective maps between them, and hence subfactors. All you're left with when you're studying maps between factors is unital inclusions of the form A inside B. Now, to make this concrete, you can just think about a finite dimensional example where you unitally embed 2x2 matrices into your 4x4 matrices. Or you could as well go infinite dimensional, where here we'll be looking at group actions on what's called the hyperfinite 2-1 factor. So what is this? Not to make you too scared. We really won't be discussing too much analysis here. But you can think of R, the hyperfinite 2-1 factor, as non-commutative analog of a probability space. So you can think of for instance, L infinity functions over the 0-1 interval, compact interval, but now a non-commutative analog of that. So this is an infinite dimensional space, which has some notion of a trace, right? It has some sort of non-commutative probability measure. And you can characterize it as the smallest infinite dimensional factor. That's why this guy here is super relevant. There's many characterizations of it. And we typically call it the hyperfinite 2-1 factor. Now, if you have a group action alpha of a group gamma here, you can craft a subfactor by looking at the position of the fixed points of the action inside your hyperfinite R. But also you can somehow implement this action into a larger or an extension of your algebra R via what's known as the cross product construction of gamma by alpha, depicted right here. So what happened in the early 80s is that Von Jones introduced the notion of index for subfactors, which basically tells you, right, if you regard B naturally as a module over the subalgebra A, it basically tells you how many times you can fit A inside B, plus perhaps a small projective part. So you can, of course, have some fractional notion of dimension of B over A, and we will call it index. And then he showed the striking result that the values this index can take do not vary continuously all the way from 1 to infinity, but rather the set is split in two, where you have a discrete set starting 1, 2, and converging all the way to 4, and then every set of points between 4 and infinity is allowed. But not only that, he went ahead and constructed a subfactor of the hyperfinite 2-1 factor for each allowed value of the index here. And one of the many ideas that Von developed in this paper here is what's now known as Jones's basic construction, where basically just from the data of an inclusion of A inside B, if you adjoined into B the projection that takes B down to A, and you can canonically enlarge this algebra into a larger factor B2. And the key observation here is that if you look at the index of this green inclusion here, that is maintained. So if you look at the index of this gray inclusion, you get an equality here. And actually what you get is some multiplicative index. And what you can do here, maybe to concretize these ideas, is to think as field extensions in Galois theory, again, made non-commutative, where you have some notion of a multiplicative index. And to justify the choice of notation index, one could, for instance, carefully study the examples of group actions and actually reconstruct the notion of index for a subfactor, but now in this context. That's just to give you somehow the spirit of what these constructions are. Hopefully I'm conveying the idea of this. Yeah.
So just can you give an intuition why I should therefore expect a non-natural number as an index?
I mean, I guess I can answer your question with the fact that they exist. So for instance, if you get a fractional index, 4.5 or something like that, this means that B is, say, a direct sum of A 4 times, plus some projective cut down of A. So if you regard B as a projective module, you get four copies of A plus a projective corner. And since you're in a probability space or in a tracial von Neumann algebra, that index is really measured by the trace of the projection defining your little corner over there, if that makes sense.
I see, but this never happens for finite dimensions. It's only because like projections in infinite dimensional space, you can probably like find sequences of like ones in certain matrix positions that converge to like, I don't know, well, I'm not really sure how to think about it, but
in a 2-1 factor, you can find projections of any trace, right? Which is not the case in many algebras, particularly finite dimensional ones. And something that also wouldn't happen, say if we were here just looking at group actions, we would only get integral values of the index, right? So what I'm trying to hint here, and I will come back to it later, is that group actions are just particular instances of symmetries. So everything that's not integral has to mean something. So that's sort of the context we're at. But let me not get ahead of myself. So what happened with this introduction or with this invention of von Jones of the index is that this really started the modern theory of subfactors and all this industry about subfactor classification by index. So how to study a subfactor? There's many approaches to it, but the one we choose is that of the standard invariant, which is simply the lattice of higher relative commutants, which is constructed as follows. Let me slide back up a little bit. So if we go back to Jones's basic construction, there's really no need to stop here. You could as well perform the basic construction into this gray inclusion and get an algebra B3, and then again B4, B5, all happening at the same index. So what you end at the end of or perhaps if you repeat this process indefinitely, you get what's called the Jones tower of fixed index, right? It's all fixed by the initial inclusion. So this standard invariant will be constructed by computing the normalizer algebras or just the commutant of A inside each of the larger algebras. So for instance, the first row here in blue is just the centralizer algebra of A inside of A, the centralizer algebra of A inside of B2, and so on and so forth. And then the second row is just doing the same process, but now for B. And the lattice of inclusions here is easily obtained just by playing around with properties of commutants. Now you can ask yourself, why only 2 rows? Why not just adding another row for B2 and B3 and so on? Eventually, at step 2, you would get some redundancy. So this is really all you need. Now this blue structure here, the standard invariant, is so rich in structure that it can be formalized or presented in very many ways. For instance, and one which we will not touch upon is Ogniano's formalism of paragroups, but perhaps more relevant to us is there's serene pulpus lambda lattices and commuting squares. And here, very concretely, you're being shown a commutative square of finite dimensional C-star algebras. Also relevant to us is Jones's planar algebras, and mainly the reason that brought us here is one can present this structure as a unitary tensor category. Now, to help me walk you through these 3 last bullet points, I really have to speak about reconstruction. Where Serene Pulpa back in '95 was able to show using hard functional analysis that every such lambda lattice, aka standard invariant, arises as decentralizer algebras for some finite index subfactor. And then a few years later, together with Dmitry Slektenko, showed that any standard invariant can really be achieved using subfactors of the free group factor, LF infinity. Now, if this is all kind of out of your orbit, don't worry too much about this, put it on the back of your mind. We will revisit these results and perhaps reinterpret them in a more accessible language for us. Now, what's really key for us is Guillaume Jones's and Slektenko's reproving Pulpa's reconstruction theorem, but now instead of relying on functional analysis, what they used is planar algebras and free probability. And this will be key for us. I will actually come back to their construction and use it to construct symmetries of C-star algebras. But let me come back from the air and land in a very concrete example. What I want to show you now is how to achieve this standard invariant as a concrete unitary tensor category. So all you need to start with is the data of an inclusion, and then you can really craft that long canonical tower, Jones's tower. And the idea here to guide the construction is looking at all those higher algebras as bimodules over A and B, varying the flavors, maybe looking at AA, AB, BA, BB bimodules. And so taking the cue from the blue invariant I showed you before, which I brought back here, we can arrange the endomorphism algebras of all the bimodules appearing in the Jones tower, where, for instance, and here, before I start, let me just explain what this Gns construction is. This is just a construction in representation theory where basically you represent B acting on itself by bounded operators faithfully. For any practical purposes, you can just think of B, L2B as B itself. That's just an analytical jargon. So every time you see L2B, you're safe to think I'm speaking about B as a bimodule of itself. So coming back to the blue lattice here, well, really we can identify endomorphism algebras of the bimodules appearing as the relative commutants. So if you look at A as an AA bimodule, this endomorphism algebra actually corresponds to the center of the algebra A. Now, if you look at B as an AB bimodule and look at its endomorphism maps, AB bimodular maps, sorry, what you recover is this blue algebra. And you can keep on doing that. So for instance, here, if you look at B2 as an AA bimodule, you would recover this centralizer algebra. For B3 as an AB bimodule, you would recover this centralizer algebra. So if you walk from left to right, you see that we're playing with induction and restriction from A to B at each step. We're varying the flavor AB to AA, AB to AA, and so on. And really to unveil the tensor structure behind this construction, perhaps I convinced you so far that there's a category lurking on the back, right? But where's the tensor product? Well, with some work, one can show that, say, for instance, the first step in the basic construction arises as a tensor product. This is formally known as confusion So it arises as a tensor product of L2B viewed as an AB times its dual, right? And the dual of B as an AB bimodule is just switching the actions, right? It's just B as a BA bimodule. And this tensor product is simply, you can think of as an algebraic tensor product where you're balancing out the middle A action. And you'll find a similar structure for B3 and B4 and so on. Well, we focused on the first row too much. So the second row is really constructed in the same way, where you start with B as a BB bimodule, then look at it as a BA bimodule, and then look at the basic construction as a BB bimodule, and you actually discover it's again a tensor product, and keep going on. So if this was a little bit involved and convoluted, let's take an abstraction step and maybe look at from far away to see what happened. But really the punchline here is that what we cooked up here is a unitary tensor category with a generator, which happened to be L2B as an AB bimodule. Of course, we allowed for direct sums, and the tensor product is confusion, or just a relative tensor product, and you have a duality structure. Right? This duality structure showed up naturally when we studied the structure of the basic construction. So abstractly, we can characterize a standard invariant as a triple consisting of a unitary tensor category, an abstract tensor category C, with a chosen generator X, and then you fix a representation of the category. So basically, you realize your abstract category as a full tensor subcategory of the tensor category of bimodules over your algebra A plus B, right? So, so basically, this representation here allows you to interpret each of these endomorphism algebras just as endomorphisms in your category. So what the abstract phase or the abstract presentation of a standard invariant is just looking at this completely algebraic construction of different inclusions of larger and larger endomorphism algebras. So for instance, if you're moving from left to right on the first row, you're alternating multiplication by x and x dual, and same goes for the row on the bottom. And if you intend to move from the bottom to the top, basically you have to multiply by the identity on x, right? So for instance here, if you multiply this endomorphism algebra by x on the right, I think I said left, I meant right, you would recover this full endomorphism algebra. So this is just an abstract presentation of a standard invariant, but we can actually take an extra step and now formally define an action of a unitary tensor category on a star algebra A as a full and faithful tensor functor from your category into the bimodule tensor category over A. And perhaps if there's no objections, maybe up to this point, you can agree that this would be sensible to be defined as a representation, but maybe ask, why am I choosing to call this an action? So let me justify that. And I'll do so by means of examples as well. So for instance, if you start with the data of an action alpha of a group gamma on a star algebra A, really with little effort and all with canonical information, you can promote the data from this action into a functor of this form, call it alpha again. But now the tensor category you would get is the UTC of gamma graded finite dimensional Hilbert spaces. So an action in this I guess in the regular classical formalism does mean a functor of this form. Now, moreover, and perhaps relevant to the coherence data that comes with a tensor category, operator algebras often care about what they call twisted actions. So you have a group and a twisted action on an operator algebra. And the twisted actions do fail to be an action, right? It's not explicitly a group homomorphism, but to the degree that requirement fails can be measured by two co-cycles in the group. So for instance, if you have a twisted action, if I can write something, if you have a twisted action, twisted by some two co-cycle, what you'll be able to promote this to is to a tensor functor out of the category of gamma graded Hilbert spaces, but the associator is now twisted by the two co-cycle. And then you can really leverage the information of a two-code cycle you can really deem it as equivalent to the associated data for the category. So here you will get BIM-A as well. Now, with regards to reconstruction, whenever you have,
I'm sorry, Roberto, I'm sorry. Could you say a bit more on how to extend actions to actions of groups or twisted actions into, these actions that you have here?
Are you interested in the twisted case or the untwisted case?
Yeah, in the twisted case, I suppose they're both mostly the same.
Yeah, I mean they're the same. So let me just stick to this one, and I'll just tell you what bimodules you get. So for instance, here you can really embed your group here, and what the functor does is maps G to a bimodule AG, and you view it as an AA bimodule. So now the actions on elements of this form, for instance, let me just call them A and A2. You simply define them using the multiplication on A on the left, and then you twist the multiplication. I think here you want gamma inverse, or sorry, G inverse, or G, one of the two, by A2. So that's how you do it. Now, with regards to this guy here, gamma, you would have to realize at some point that the coherence data for a tensor category, if you interpret the pentagon equations in the context of a group and a co-cycle, the co-cycle equations and the pentagon are actually the same thing. So that's I'm just trying to guide you through the answer on the twisted case, if this makes sense. Yeah, sure. So
actually, so is the definition of a gamma action on A given by the thing you wrote underneath it, a functor from Hilb gamma to bimod, or was there a previous definition and you're saying this is equivalent to this one?
No, what I'm starting with here is just the classical notion of a group homomorphism of an action, which is basically a group homomorphism from gamma into the automorphisms of an algebra. So
right.
every time.
So what is AG?
AG as a vector space is just A. I'm just denoting that you're twisting the multiplication on the right by the group action.
Okay, got it. Thank you.
Yeah. That's what. So basically, we're promoting this formalism to now a tensor categorical formalism. Well, now in regards to reconstruction and going back to cross products, for instance, if you have a standard invariant as I'm presenting it, you can also craft extensions of your algebra A by means of some generalized cross product constructions, where instead you would use your F as an action here, right? But I think earlier I was writing something like this. Right, but now the place of the group that I had here is played by G, where G is some algebra object in your category. So there's really a strong analogy between the methods and examples that work for groups, but now in a more general context. So I hope this justifies me saying that subfactors do have quantum symmetries, which are much larger than just classical group symmetries. And I think this is a good moment to stop for more questions from the audience.
I didn't get that last statement you said about these quantum symmetries. Are you saying because we're looking at the entire category of bimodules over A instead of just A, or what? No, because for instance, going back to Von Jones' work, you could actually create one of these functors at any index using the hyperfinite 2-1 factor. And if you were restricting yourself to groups, you would only achieve integer values of the index. But of course, there's everything else, which is most of the allowed values for the index. So here you have a formalism that encompasses all of group actions, but of course there's most other things. If I comfort you, I hope I comforted your question a bit. Well, I don't know. Maybe I usually think of a symmetry as a morphism in some category, preferably invertible. So what's the symmetry?
What is the
symmetry? I mean, an index is not a symmetry, so I guess I'm still a little bit confused. Usually I think of a symmetry as a morphism or an automorphism or a equivalence of categories or something that's kind of invertible. Homotopy equivalence, something.
Yeah. Yeah, take this. And yeah, you'll have to relax the notion of invertibility. And I guess the analog of invertibility for groups is now the duality axiom for unitary tensor categories. So really what you want is to have a bimodule and its dual. So really, so I think you're really demanding for unitarity deep down. I think that's what you're asking.
I see. Okay, thank you.
Yep. Yeah, sure. Thanks for the question. Okay, so I think we're approaching
sorry,
now.
Roberto, sorry, so in that direction, how does so you're saying that the symmetry comes from the fact that you have so duality on your UTC, right? And so how does that act on bimodules? Or I mean, how does that get reflected on the category on the right?
So here I'm hiding really all of the structure you want here for there's time constraints, but really what you want here, I think in all its glory is, I cannot erase for some reason, OneNote is betraying me. But here what you want is a bi-involutive functor. So really what you have in these two categories is two involutions, one coming from the C-star algebra structure on the endomorphism spaces, which diagrammatically you can view as a can you see my fingers? As a reflection with respect to a horizontal line. And the other involution is a conjugate linear extension of reflecting your diagrams in this direction. So you want your functor not only to play out well with the categorical structure, with the tensor functor, but also with those involutions. So really in all its glory, I should have said this is a bi-involutive, fully faithful, strong monoidal functor. I think that's what I want.
Okay, thank you. That's very nice. Thank you very much.
Yeah, thank you for the question. Okay, so now hopefully I've made my point. Subfactors have quantum symmetries. So now let's start transitioning to C-star algebras. And I guess the first question one could ask is, well, do UTCs even act on C-star algebras? And I guess historically there's been some examples. The answer is yes. There were some examples back in the 90s, constructed just out of thin air, kind of surprisingly by Izumi. We're using some idea from quantum field theory and techniques from type 3 factors. He managed to construct actions of categories on different Kunz algebras. So for instance, he managed to put the Fibonacci category to act on the Kunz algebra on two generators, where here phi, for instance, is the Fibonacci category, has two objects, the monoidal unit and tau, where the categorical or quantum dimension of tau is actually the golden ratio. So here you have an example of a non-integral category acting somewhere. And he did so just by constructing specific, he was very concrete about using endomorphisms of, I think it's a type 3 one factor. And then he built some other examples. I think another one that's relevant for us is the representation category of S3 acting on the Kunz algebra on three generators. And well, we had to wait for like 25 years or something for Yuan to appear and construct an action of any given unitary tensor category on some C-star algebra. And the C-star algebras he managed to construct happen to be non-separable, which, I mean, I guess he's showing an existence point, but one would at least want separable C-star algebras because they're simpler to work with. So before fully transitioning into more or focusing completely on C-star algebras, let me just put the two perspectives in contrast, right? For von Neumann algebras, by reinterpreting this results by Popa and Shlaktenko, and in this new formalism, we can interpret LF infinity as a universal receptacle for actions of unitary tensor category. So any UTC will act on the same two-one factor, LF infinity. So you can ask the question, for instance, is there a universal receptacle for actions of unitary tensor categories, but now on the C-star algebra field or on the C-star algebra side? Well, the answer is no. There's K-theoretic obstructions that just don't allow for it's just impossible to have that. And particularly, you would want a monotracial, separable, and unital C-star algebra, somehow resembling factors. So such an algebra is too small to fit symmetries coming from all unitary tensor categories. There's too many unitary tensor categories. So such a universality result here just wouldn't hold. So what I will show you now is a theorem where we improve UN's results in the sense that we can build a concrete C-star algebra that's separable. So for every UTC, we'll be able to craft a UTC action on some GJS C-star algebra. And later, we will use that theorem as to state some weaker universality condition here. Okay.
I'm sorry, Roberto. So could you give an example or a non-example of a monotracial separable C-star algebra?
Yes. So, for instance, if you go up here to our standard invariant, I'm not sure if you can see my screen because I cannot hear. Where we have this horizontal inclusion of endomorphism algebras, right? You can construct an inductive limit C-star algebra in such a way that the trace. So if you want the trace on the limit to be compatible with the trace on each algebra at each stage, you'll get a unique monotracial C-star algebra. I will bring in a super relevant example at the end called the Yangtze algebra, which is also monotracial. By the way, these algebras are known as AF algebras. And I also didn't say it, but one of the reasons that von Neumann algebras have so many symmetries is that whenever you arrange for a chain of this form, the limiting von Neumann algebra you will get is always a hyperfinite 2-1 factor. It doesn't matter what C-star algebra, what finite dimensional blocks you put, you'll always get the hyperfinite. For C-star algebras, you not only get dependencies on the algebras, but also on the connecting maps. So here, C-star algebras already make a mess. And a non-example of I guess a non-monotracial C-star algebra would be, for instance, O2. You have no traces. So you can either have 0 traces, 1 trace, or just many traces.
Okay, thank you. Thank you.
Yeah, sure. Where was I? I was about to show you this theorem. So yeah, last year, together with Mike Harlows, we managed to show that every tensor category, unitary tensor category, will act on some simple, separable, unital, and monotracial C-star algebra constructed out of the category using the methods from Guione, Jones, and Sliertenko. So I guess concisely what we did is, given a UTC, we constructed a representation of C into the bimodule category over that GJS C-star algebra. And I will not show you the proof in all its glory because it also takes some techniques from analysis, but I do want to walk you through it and perhaps walk you through the ideas that go into it. So let's start with a proof sketch. And I guess now we'll move horizontally so that you guys can see a bit more for longer. So how do we craft this representation? You start by fixing a generator of your UTC. And well, now with regards to your question, Juan, we'll craft an AF C-star algebra just by taking the inductive limit C-star algebra out of the one of the rows of the standard invariant and call that algebra A infinity. Realize that all of this is canonical to the category. I'm not asking anything extra. And what we will do now is we will build a graded tracial star algebra with the structure of an A infinity bimodule. So as a vector space, this graded GR infinity algebra is just the sum of over non-negative B, L, and R of the Hom spaces connecting X times B with X to the L times X to the R. So again, using the graphical calculus or appealing to it, a generic element of this big sum here just looks like a diagram with B legs, L arms on the left, and R arms on the right. And the algebraic structure is very diagrammatical, very natural. So if you want to multiply a square by a triangle, you simply ask if the number of strings match. If they don't, you get 0. And if they do, what you'll do is put them together and join strings on the bottom one by one until you either exhaust B or B prime, and then add all of those diagrams. So that's a legit operation. Now, for free also, we get a trace. So the trace of a diagram, for instance, is just taking the 0th graded component and then capping off the strings on the left and right. Of course, if L is not equal to R, you get 0. Now, this diagram here indeed represents a complex number, right? Because using the graphical calculus again, this is an endomorphism of the monoidal unit, which we assume to be simple. So this trace really takes us from this algebra down to the complex numbers. There is an involution on this algebra, and actually apropos the earlier question on bi-involutiveness, I didn't draw it here, but there's a star operation here where basically you reflect vertically and then rotate by 180 degrees, using all of the duality structure of the category, really. But I will not draw that. Now, as for the A infinity left and right actions, we'll just take a generic element in your A infinity algebra, A, and another one, A prime, which you can diagrammatically depict in this way, and the action is merely concatenation. So everything that's happening here is algebraic and diagrammatic. And now let's do some analysis. Because in this bimodule GR infinity, we can somehow lift the C star algebra norm to the whole module. So I will really not go into the details there. But what you can do with that is then complete your module in that C star norm. And what we will do next is identify this now complete in some norm bimodule with a full Fock space, which is really a full Fock space generated by the diagrams, or those diagrams having only one string on the bottom. And formally, that is just putting together, or say, direct sum of strings with diagrams with no strings on the bottom, and diagrams with one string on the bottom, then two strings, then three strings, and so on. So this isomorphism here is actually not too hard to believe. And what this really does for you, besides stating something somewhat intuitive, is that we can really regard multiplication as a bounded operator in terms of creation and annihilation. And that has very many analytical advantages. So using the trace, the diagrammatic trace I described, and the aforementioned GNS representation, we can faithfully represent the family A infinity together with all those creation operators by self-adjoint elements in the algebra. And we faithfully represent them in the algebra, or the star algebra of bounded operators on the bimodule. So we're acting on our bimodule by multiplication, in this case by bounded multiplication. So you can think that we have embedded our algebras in some space of operators, and there we can take a C star completion, or take a C star norm. And what we get at the end is a C star algebra B infinity that contains A infinity and all these weird operators. You can forget about them. And this is not really the algebra we want to use for a representation. But what this is, and borrowing some terminology from free probability, this happens to be an A infinity valued semicircular system. So what this comes equipped with is a faithful conditional expectation from this larger algebra into the ground algebra, A infinity. And of course, composing with the trace, what we get is a semi-finite tracial weight, which will be relevant in a second. For now, let's compress this B infinity system, because it's really out of B infinity where we will find our algebra B naught, the GJS C star algebra, and the bimodules we will use. So just using the operations I defined in GR infinity, one can show that for each n, the projections, well, the diagrams Pn of this form are actually orthogonal projections. So that's just a matter of computation. And what you can do is consider the L-rth corner of B infinity simply by compressing the system. And again, intuitively, this is a Banach space which densely contains all those diagrams having fixed number L and R strings on the left and right, and just arbitrary, just an arbitrary number of strings B on the bottom. Of particular interest is the corner B naught, or 0 B naught, where you're basically compressing to keep all those diagrams which have no strings attached to the left and right. So it's just guys without arms, I guess. That's how you can think of them. So diagrams without arms. Now paying special attention to the corners 0 of the form 0BR or 0BN, what's really useful for us is that if you fuse, say, the 0BN corner with the 0BM corner over B naught, there is an obvious action of B naught, where, for instance, you can just, let me draw it quickly. You can just simply put boxes here or there, and that's a B naught action, again, understood diagrammatically. So if you fuse them over B naught, the resulting bimodule you get is again in this family, and it's actually unitarily equivalent to 0 and to the 0th n plus mth corner. So just put that in a box, keep it for the record. Now let's explicitly construct a representation. right? So we're ready. We have all we need because what you'll do to represent your category as bimodules over this corner B naught is just take the rth tensor power of your generator and map it to the 0th corner. And then if you take a morphism in C going from, say, x to the r to x to the r prime, diagrammatically represented this way, you'll get a morphism FF that grabs a diagram with 0 arms on the left and r strings on the right and just concatenates F, and of course lands on the right space. So just by construction and directly, one can show that this functor is faithful. And if you stare at this equation or this isomorphism for long, you'll be convinced that this defines a tensor functor. And being a tensor functor in this context means this. However, showing that this functor is full does require some more analysis. It's not an algebraic conclusion one can simply take. So the last step of the proof, I think, will be to show that the functor is actually full. And I will not do it for you, but again, I hope I can guide you through the ideas. And the technique we use is to Hilbertify our C-star bimodules. Where basically we think of them as Banach spaces and we do something to them that turns them into honest Hilbert spaces. And we can actually do so in a monoidal tensorial way, where basically we just grab a bimodule and tensor it on the right by L2B naught. So let me put all of the information of this proof in a single diagram and summarize what happened, right? So we started with a UTC-C and then built a faithful representation, a faithful tensor representation into a category of bimodules over B naught. I'll tell you what those adornments mean in a second. Keep that question for a second. And then this Hilbertification functor here, horizontally on the bottom, just grabs a bimodule over B naught, Y, and tensors it on the right by B naught, right? So where we would want this image to land is in the bimodule category of M naught, where M naught is the von Neumann closure of B naught. So again, B naught is some C-star algebra. If you take its von Neumann algebra closure, you get M naught. And you can actually characterize this algebra here as the 2-1 factor corresponding to a free group factor. So B naught really resembles a 2-1 factor in a very strong sense. So what you would need actually to construct this arrow and say you have a nice bimodule here is to extend the B naught left and right actions to actions of the von Neumann enveloping algebras. And that step is highly non-trivial. It's actually impossible in general. So what saved the day here to make this arrow work is that this functor F here does lie in what we call tracial bimodules. So luckily these corners are tracial in the sense that how to put it simply, the bimodule structure is compatible with a unique trace on the C-star algebra B naught. And I forgot to say that, but that semi-finite trace we got on B infinity descends to a unique trace in B naught. So what we want is bimodules that play out well with a unique trace in B naught. So once you've done that, you'll be able to extend these C-star algebraic actions to von Neumann algebraic actions. So that on the one hand. On the other, back in 2013, Brodier, Hartglass, and Pennies constructed a fully faithful representation of C into this category directly. However, since they were using von Neumann algebras, they were indeed able to show that this functor is full. But the fact is, if you compose F with a Hilbertification functor, what you recover is exactly this arrow. And since we're just dealing with finite dimensional algebra when we look at Hom spaces, because our categories are unitary, the fact that this functor is full and that this diagram is commutative implies that F must be full. And that's just a single application of finite dimensional C-star algebra. And that's the punchline. That proves the theorem. Since this arrow is full, F ought to be full. QED. So that's it. So basically, this shows that given any UTC, you'll be able to craft a GJS C-star algebra and an action on that C-star algebra. Now I'm waiting for my own screen to refresh. Hopefully, it doesn't take too long. Well, I guess what I want to continue. Can you guys see my screen? Mine is completely blank. Interesting. So I'll just guide you blindly. So the next result is really a weaker form of the universality, right? So again, for von Neumann algebras, LF infinity is this universal receptacle for quantum actions. But there is no C-star algebra that admits so many symmetries. However, if you do restrict to unitary fusion categories, right? If you only look at essentially finite tensor categories, well, there's just countably many of them. So you can take the free product of all these unitary fusion categories, and the tensor category you get at the end is again a unitary tensor category. So you can just implement this results in to that product of all the unitary fusion categories and craft a universal GJS C-star algebra that admits an action from every UFC. This is giving me some trouble because it's still not refreshing. Let me stop sharing for a second. Is that doable? And see if I can do something about it. I guess questions so far. I can see again. Can you guys see this now? Good. Yeah. So this is the weaker universality I was trying to state. So basically, we can claim that every unitary fusion category acts on the same GJS C-star algebra. So we have a universal receptacle. I guess this sort of saves the day for C-star algebras. So these are really all the results of mine I wanted to share today. I want to close my talk with perhaps describing what are the perspectives of the field. And also, I told you I would justify why should you care about this. And I guess the main reason is that the classification of nuclear or amenable C-star algebras was recently achieved by many hands. And you can really compare that classification to what Kahn achieved in the 70s, when he classified injective factors. Right? So now there is a classification of all nuclear or amenable or nice C-star algebras, which only occurred like 45 years after or 40 years after the classification of injective factors. And I guess what I want to do now is perhaps sell a little bit what my research project or my research program is in light of this classification by comparing features of these two programs and then perhaps drawing an analogy. So for von Neumann algebras, really the classification occurred up to R stability. So you would be able only to classify infinite dimensional factors which absorb R tensorially. So you would want to classify factors M such that multiplied by R, you didn't change the factor.
What is
so
R?
this is, go ahead.
What is R?
The hyperfinite 2-1 factor. So let me remind you here. This is the smallest infinite dimensional factor. So this classification is really occurring up to R stability. So up to those factors which absorb tensorially the hyperfinite 2-1 factor. On the C-star algebra side, the class of C-star algebras can only include those which are Z stable. So you can only classify algebras A, which tensorially absorbs this algebra Z, which is known as the Yangtze algebra. So this Yangtze algebra is very special because in K theory, it's like an infinite dimensional analog of the complex numbers in the sense that it has the same K theory. It has kind of trivial K theory. So it really plays the role of an infinite dimensional copy of the complex numbers. And as well, it can be characterized as the minimal self-absorbing C-star algebra. So for instance, you'll get identities that look like this, right? And every time you do this, you can put any group to act on the Yangtze algebra, for instance, just by permuting the factors, any finite group really. So what I'm trying to convey here is that the analog of R, or there is an analog of R in both classification programs, which is the Yangtze algebra. And of course, R is somewhat well understood from its from the perspective of quantum symmetries. However, the story with the Yangtze algebra is completely different, right? Again, K-theory comes in the way in forms of obstructions. So since the K-theory of this guy is very poor as compared to the K-theory of the hyperfinite, you will only be able to find actions of unitary tensor categories which are integral. And these include, for instance, twisted groups or representation categories of finite groups. But something like Fibonacci or something alike that I presented before, you won't be able to find quantum symmetries here, just by K-theoretic considerations. And actually, just recently, it was Evington, Hiron, and White who showed that if you can find an action of twisted vector spaces, G by some cocycle omega on the Yangtze algebra, it means that your cocycle is actually trivial. So it leaves the question open, right? We don't really know anything about the Yangtze algebra or classifiable quantum symmetries of classifiable C-star algebras. We know nothing, right? So the question that just opens up is really to know what are the quantum symmetries of the Yangtze algebra. And the next natural question you can ask, as simple as it is, to my knowledge, no one knows the answer, is whether the representation category of S3 act on the Yangtze algebra or not. That just isn't known. And I guess another interesting program one could pursue out of this perspective is to understand, say, reconstruction on the C-star algebraic setting. And this is asking, can I characterize, or which C-star subalgebras can I characterize by a standard invariant? So this is it. I think this is everything I wanted to present today. Thank you so much.
Thank you so much, Roberto, for the great talk. It's really interesting. Are there any questions or comments for Roberto?
I have a small question here. Could you say a bit more about this Fibonacci category? You went pretty fast. You just said it has two objects and so on.
Yeah. So hopefully my screen is not freezing again. Where was this? I think here. Yeah. So this Fibonacci category, which also has its relevance in condensed matter physics, by the way. People use it to model quasi-particles and stuff like that. I'm not good enough to speak about that, but at least just from a dry viewpoint, the Fibonacci category, you can see it as spanned by the monoidal unit and some object. And why do we call it a Fibonacci category? Because you ask for this relation to hold 1 plus t.
Okay.
So that's what make it Fibonacci. And now what's really weird about this category, or at least what makes it non-integral, is the following, right? If you have any you have a reasonable notion of dimension on unitary tensor categories, but whatever that is, it must be a ring homomorphism to the complex numbers, right? You want a multiplicative additive notion of dimension, right? So what should the dimension of t be, of tau be? Should be a solution to this equation. So it means that you can choose either of these to be the dimension of tau. And actually, by hand, one can show that this tensor category exists, which would be, I mean, that would be a reasonable contest to this setting. But yeah, one can show that this category exists. One can exhibit the associators, and one of them exists actually for each choice of sign here. I think one of if you choose the minus sign here, it's not a unitarizable category, but if you choose a plus sign, you'll find a unitary structure there. So that's what it is. Yeah, I think it also became important in the classification of categories of say fusion categories of small index. I think there's a paper of Ostrich about fusion categories on rank 2 that you can look at if you're interested. Basically classifies rigid categories of having two simple objects. being one of them.
Okay, thank you.
Yeah, sure. Thank you for the question. I guess I didn't say it, but at the end I prepared a section for the bibliography that you can go enjoy at your own leisure. I think these are all the references I used. So hopefully you find one of them interesting and want to go take a look at them.
Yeah, Carlos has a question. Yeah, please go ahead, Carlos.
Thank you for the talk. Nice talk, Roberto. My question is about this this dictionary that we have in non-commutative geometry, that we go for the geometric side and then we have something like that. Studying with factors and the construction of unitary tensor categories, there is any application to orbitals? Yeah. And also another is that maybe not, but if there is a relation with fractals.
Okay, so I'll answer your questions in order. No and no. I don't know. I don't know and I don't know. That's my answer to both questions. But let me try and say something. I really do not know what's the relation here to fractals. Maybe we could chat later if you have something in mind. I'd love to hear about that. I've no idea. I've never heard the words together, fractal and UTCs at any point. But for orbifolds, I'm not sure what these are either. But there is a notion of orbifold completion of a two category. And I'm thinking of work of Ingo Runkel, where basically it's some form of higher idempotent completion of a two category. And the point is that if you want to somehow parametrize extensions of a factor by categorical data, the relevant categorical data that will play a role are called Q systems. So in regards to orbifold completions, I think that a Q system completion, which is somehow, I'll just put it as a higher idempotent completion of a two category, corresponds to these orbifold completions. And I've seen those used in the realm of topological quantum field theory, but that's really all I can say about them. I'm not sure if you have anything specific in mind, maybe to help me out a bit.
For example, when you we have a global orbifold, let's say that you have a manifold and an axion of for example, a Lie group. Then you can construct the cross product. That's the group algebra across the I think the sister algebra associated to the manifold, and then you have just a sister algebra. With that, you can make all the construction you mentioned in the talk.
Yeah, I don't think there's anything certain I could say in that respect. There's also a recent paper by Corey Jones. I'm not sure if you're aware, called I think it's Remarks on Anomalous Actions of C-star Algebras, where he, for instance, finds quantum symmetries of classical spaces, right? So these apparently different two notions. I mean, they're it's not trivial. Let me put it this way: it's not trivial to find a quantum symmetry in classical spaces, or at least in a connected classical space. So in this paper, he cooks up some of these actions, and in regards to your question, I think he manages to find actions of UTCs on C-star algebras that are C-star algebras associated to 3 and 4 manifolds in some sense. These row algebras and has some relations to coarse geometry. Unfortunately, I cannot be too precise at the moment, but hopefully you decide to go look at this paper and find something useful. But that's I think the closest I can get to giving you a useful answer here.
Okay, thank you, Roberto. We can talk later.
Sure, I'd be happy to. Thank you for the question.
Are there any other questions or comments?
I think I still have maybe one or two small questions.
Mhm.
One is very broad. So you outlined some, I think applications is as far as I understand them, of the fact that every unitary tensor category acts on some C-star algebra, or every C-star algebra admits an action of a unitary tensor category. I can't remember which of those two results was the conclusion, but I guess I'm trying to understand the bigger picture of are we trying to use this result to study the structure of that given C-star algebra or its inclusion? Like, what exactly are you trying to understand by looking at these actions? Are you like, at some point you mentioned the classification theorem, but that theorem was already known before your results, so I'm not really sure what you use it for.
Yeah. So I guess I put everything together at the end. So let me try and separate things. So for instance, with regards to your confusion on whether every UTC acts on some C-star algebra or the converse, yeah, I guess the point is, out of every tensor category acts on some C-star algebra. That is a punchline theorem, and something that wasn't known was whether you. I mean, at least in that generality, is whether that algebra is separable. For instance, like some earlier constructions use some very highly non-separable spaces. So that's a desirable property. Gns C-star algebras, for instance, are not classifiable. They're exact, so they're close, but they're not nuclear. So there's still many things to do there. But I guess in the regarding C-star algebra classification, what we want to understand is perhaps the structure of classifiable C-star algebras from a quantum symmetries viewpoint. And for instance, here with the Yangtze algebra, what I'm trying to highlight here is that there is a deep connection between the structure of this algebra, say in terms of homotopy invariance, K-theory, and the type of quantum symmetries that it admits. Right. So similar to what you would do with like classical dynamics, when you have a group acting on some space and maybe you realize it's a cross product of some simpler space, you can hope for results such as those. And for instance, also if you have a classifiable C-star algebra A, which of course will be isomorphic to Z, then for instance, if you found an interesting quantum symmetry of Z, of course you can just found an interesting symmetry of A. So for instance, this classification of C-star algebras, I guess the barcode of classifiable C-star algebras is called the Elliott invariant, which is I think a sextuple of ordered groups and traces and stuff. But for instance, there's no well understood relationship between, say, the possible quantum symmetries of an operator algebra and its Elliott invariant. So how would quantum symmetries deal with the Elliott invariant, or how would they match? I don't think there's, even in the simplest AFKs, so the hyperfinite C-star algebras, I don't think there's well enough relationships there. So there's a lot of structure to unveil there, not just of particular algebras, but maybe the class of classifiable C-star algebras. That on one hand. On the other, I mean, you can ask yourself, like, why is this lattice called a standard invariant, right? You would want a standard invariant to characterize an inclusion of algebras, right? And even for von Neumann algebras, that fails. You have to restrict to some very nice corners of the theory to have like exact characterizations, right? Perhaps hyperfinite subfactors or something like that. And I guess a broader class of subfactors, which are well characterized by an abstract standard invariant, are called discrete subfactors, where, for instance, you have some very general form of a Galois correspondence of the extensions out of an initial algebra. In terms of what I mentioned earlier, were algebra objects in a category. However, the notion of a discrete inclusion for C-star algebras is not well established. I guess in plain terms would be what families of C-star algebras can be classified by a standard invariant. So those would be, I would put them as parallel programs in a sense, right? I somehow put them all together in my last line, but hopefully I'm clarifying the picture by saying this.
Yes, thank you.
Thank you.
Yeah, thank you very much, Arthur. Are there any other questions or comments? Well, I do have a small question. I'm not sure if, yeah, me too. I don't know if well, so you said that, so your result is that, so every UTC, so the first result that you talked about, so it was that every UTC acts on a monotracial C-star algebra, right? Mm-hmm. And there's no universal receptacle, monotracial universal receptacle for UTC actions. And of course, the Yangtze is not a universal receptacle, as you said. Is there any hope that there would be a non-monotracial universal receptacle for UTCs and actions of UTCs? And would that mean anything, or I don't know?
It's hard to say.
So I suppose my question is, well, I guess the difference. So yeah, the hyperfinite to one factor and the Yangtze seem very. So you drew a very nice analogy between them, and from classification, they seem very like they play the same role. But I don't know what the structure of the Yangtze algebra, but my guess is it's a lot more difficult to describe than the hyperfinite to one factor. So that's just like 2 lines of a definition, and the Yangtze, every time I've heard of it, everyone's like, okay, so this is the UTC, we use it for this, and please don't ask me what it is, or something like this. So in a sense, you would expect, so from your analogy, you would expect of course, the Yangtze to be the universal receptacle of something. But I don't know, so is there something out there that is sort of plays the role of, is there a hope that there's something out there that plays the role of R towards receiving quantum symmetries?
So I guess I would add to your question that there's something small enough that receives an action from just anything. I mean, this corollary here, probably it was very hard to understand because you were not seeing anything. Yeah, so basically what you can do is, let me just briefly recount the proof of this theorem, which basically tells you there is a universal receptacle for actions of unitary fusion categories. Now, unitary fusion categories are those UTCs where you have finitely many simple objects. But only finitely many, not necessarily countably, but finitely many.
Right. Yeah.
So the point is that there's countably many isomorphism classes of UFCs. So what you can do is,
then you take the direct sum, and then you get an action of every fusion. But for non-fusion, well, sorry, and then you can do the same thing for non-fusion, and then you get something that's really big or something like that. I'm sorry if I interrupted.
No, that's fine. I would suspect yes. I mean, it's not something I have done, but it's very easy to go non-separable. I mean, even here we're outside of a classifiable algebra still. Okay. I guess with regards to the construction of the Yangtze algebra, let me just compare it with the hyperfinite, right? Because the hyperfinite admits an action from every UFC, from every unitary fusion category. And it's really not hard to see that it admits an outer action from every group just by writing many tensor copies and permuting the factors. That's not hard to believe. Well, it's a stretch, but you can generalize that result from finite groups to unitary fusion categories. But here, for instance, if you just took the inductive limit von Neumann algebra of one of these rows, or both of them actually, you would get a hyperfinite. Well, this is just hyperfinite reconstruction. So you would get a hyperfinite subfactor. Now, to construct the Yangtze algebra, I mean, the construction is a bit involved, but it's not impossible you don't need to be an expert in operator algebras. What you do is, it's again an inductive limit, but no longer of finite dimensional algebras, but what's called dimension drop algebras. So basically you put, you parameterize finite dimensional algebras over the interval, and then you ask some conditions on each side of the interval, right? You get some smaller matrix algebra on one side, and then another dimension matrix algebra on the other, and then induct on these blocks. And I think initially the Yangtze algebra was just meant as a curiosity or something like, show there's an infinite dimensional analog of the complex numbers from the K-theoretic perspective, not necessarily as your monoidal unit for some class of C. No. Eventually people realized that, because I guess the initial claim by Elliot was to propose some homotopy invariance as to classify C-star algebras, right? So there's K0, there's K1, and there's traces. I think that was the initial invariant. So of course, this is a counterexample to that, because if you're only looking at the invariant up to that point, you have C, which is finite dimensional, and Z, which is not. So of course, they're not the same thing. So in a way, its discovery helped refining the structure of the invariant. I think that's one of the consequences it had. And it turned out that it was absolutely central for the classification. And with a very strong parallel to R. But if you look at their quantum symmetries, they're just, R is super rich in quantum symmetries. Any UFC will act here. However, not even twisted vector spaces can act on the Yangtze. And even this question, right? Like it's kind of bothering. Does the rep category of S3, it has how many elements? 3 elements, simple elements. Does it act on the Yangtze? It's not yet known.
Why did you ask specifically for S3? Just because that's the simplest example you can.
Yeah. I mean, yeah, that's not just VEC. Yeah. And for instance, here you have an object of dimension 2, whereas everything here has dimension 1. So you would have to look at an index 2 bimodule of that.
So what are the known quantum symmetries of Z? Well, you already have your VEC Gs, but
so far it's finite groups.
But
it's even if I mean, I don't even know about uniqueness, but I mean.
Okay.
Yeah, that's it.
Okay.
To the extent that I'm aware, of course, but I mean, this result by Evington, Giron, and White, I don't think it's even published yet.
Okay. Well, that seems very, very, very impressive, I guess. Well, I don't think I understand completely how impressive. Well, I don't know the significance of it, but I mean, for what you told us, it looks very, very cool. So just final question, I guess, from my side. I mean, okay, so I think if I understand correctly, the idea is that you can, so quantum symmetries arise as sort of generalizations of group actions on subfactors. And then you have this very natural notion of an action of a UTC on the standard invariant. And that makes sense from that standpoint. And so you tell us that, well, so you have C-star algebras, and then you have bimodules and everything. And so it's natural to consider quantum symmetries as just a step from Bonnet algebras. So who benefits from this? C-star algebras, UTCs, what is it? What is there to learn or to say, or is there, or I don't know. Well, that's my question.
Yeah.
I'm not sure if that's.
Yeah. No, I think you're touching upon something I forgot to mention. So I think I made a joke about how long we had to wait to get C-star classification. But the point here is that if you look at the development of subfactors, right? Kahn proved his classification theorem, right? He characterized this abstract notion of injectivity in terms of hyperfiniteness. And then the classification he achieved is a 1-point classification. Everything that's hyperfinite is the same thing. But then what happened after, I think, 7 years after, in '83, is Jones's invention of the index. So what happened is classification of reasonable von Neumann algebras, and then the industry of subfactors occurred, right? So you have an index. I think the classification of small index is complete up to like 5 1/4 or something like that. Of course, such a thing includes a classification of all finite groups, which is not feasible, but there's a lot of progress there. So it's really, really timely to be looking at C-star algebras from this perspective right now, because comparing their development, right, the classification just finished. So now there's going to be a huge transition, a huge migration of people in the C-star algebra communities to learn subfactors. And actually, there's a big hunt for adapting subfactor techniques and ideas into C-star algebras, precisely because how somehow subfactors led the way on what to do with star algebras. And I think many of the papers of C-star algebra classification are still under review. So this thing is still very fresh. And of course, there's this UCT business, and some people believe you can even remove more hypotheses and make it slightly better. But yeah, this is very fresh. So now there's this huge momentum gain towards looking at quantum symmetries of C-star algebras. So thanks for the question. Actually, I forgot to make that remark.
Well, I think it was sort of a rehash of Arthur's question a bit. So well, I guess, and so if you do UTCs, what's the benefit of seeing your UTC as symmetries of C-star algebra or of an Neumann algebra for that matter?
I think, for instance, now I'm really looking at benefits from or profit from the operator algebra side rather than the tensor category side.
Yeah, these can be philosophical or anything. Like you just see your UTC as some symmetries or something. Yeah. I don't know. It's very
so
basic.
Typically, I think philosophically or personally, I guess a matter of taste is that tensor category is just if you try to record it in a computer or play with it, it's just a bunch of matrices, right? With the F symbols and associators and stuff like that. So these theorems do tell you that you can actually concretize every unitary tensor category as some symmetries of some space. So I like it. I like that approach. I guess you can criticize it as useless, but it's, I guess, philosophically tells you that these symmetries do concretize.
That sounds pretty good.
Yeah.
Thank you.
But I'm not sure if there's good communication on the way back. For instance, like what can you learn about a tensor category knowing that it acts somewhere? That's a good question, actually. And even, for instance, these results by Izumi, putting the Fibonacci category acting on an algebra generated by two partial isometries, this Kuhn's O2 algebra, it's very surprising. It's of course, I guess the communication I would understand between the categorical data and the bimodules is a trace, which is lacking here. So that allows for some weird things to happen. But
Yep.
I wouldn't. Yeah. Yep. I have no better answer.
No, that's pretty good. Thank you. Well, yeah, thank you so much, Roberto. I don't think I have any other questions. Yeah, are there any final questions for Roberto? I don't want to take too much of your time with these questions.
Well, thank you. Thank you all for listening.
Yeah, if not, let's thank Roberto, and thank you so much for the great talk. Thank you, Roberto. And you're